Welcome to Elementary Algebra. The book is by Harold Jacobs. I'm your presenter, Molly Crocker. The 1979 edition of the book was accompanied by an amazing teaching manual with many ideas for engaging students. This number trick is different from the one in the introductory lesson. By the way, this material is copyrighted. Step 1. Think of a three-digit number. Keep your back to the board. You, the instructor, keep your back to the board and have a student go to the board and write a three-digit number. Write it big. The rest of the class will be checking the student's work, so they will need to be able to see it. No calculators for now. Step 2. Rearrange the digits and subtract the smaller from the larger. You may rearrange the digits in any order. I'm working an example here. Step 3. Multiply this result by any single digits other than 0. No fair. You could use 1, but try something other than 1 and not 0. I multiplied by 3. Step 4. Circle any digit in this number, in this product, except a 0, and say what the remaining digits are in any order. This is the student's job. So example, the product was 1,674, and the student might say 641. Add the digits. You, the instructor, should add the digits as the student reads them. Here, the sum is 11. Since that is a two-digit number, add the digits again. The digits of 11 are 1 and 1. 1 plus 1 equals 2. If the sum of the digits the student reads equals 9, then the missing number is 9. If the sum of the digits is other than 9, then subtract the sum from 9 to find the missing digit. Here, since the sum is 2, 9 minus 2 is 7. If you are showing the slides without the narration, then stop the slideshow here for students. Let them wonder about this. Try some more numbers. Try some four-digit numbers and happy multiplying with 4 digits. The remaining slides are for you, the instructor. Why does this work? Well, let's have a look at some number theory. Developing number sense and number theory is one of the reasons I like this text so much. These little gems and aha moments are strewn throughout the text. Let's use our example 379. If I assign A to be 3 and B to be 7 and C to be 9, then the generalized number can be written with its proper place values like this. Now, rearrange the numbers and subtract. So I'm subtracting whatever BCA is from ABC, and I don't even know if BCA is larger or smaller. It doesn't matter, actually. And then that's how it looks when I write it with its generalized form, with its place values. And now we need to distribute the negative and combine like terms. And as you can see, you have a number in which every term can be divided by 9. 9 can be factored out of this expression, so 9 is a factor of the number, of the difference of these two numbers. The difference of any three-digit number and the same digits rearranged will always be divisible by 9. Check with your calculator. 558 is divisible by 9. Now, multiplying 558 by anything, and a factor of that product will necessarily be a 9. If 558 is divisible by 9, so is a product of 558. Do you recall the divisibility test for 9? Add up the digits and see if the sum is divisible by 9. Or add the sum of the digits again, and we call this repeated addition. And if the result is 9, then the number is divisible by 9. 558 is divisible by 9 because 5 plus 5 plus 8 equals 18. And yes, 18 is divisible by 9. But if I add 1 plus 8, which is the repeated addition, then I get a 9. Since 558 is a multiple of 9, I'll say it again. So also 1674 will be a multiple of 9. Add up its digits repeatedly until there is a single digit. It will be 9. Leave out one of the digits. Don't leave out a 0. Be fair. And that digit can be found by subtracting the repeated sum of the others from 9. As long as the student followed the rules and did not choose a 0, if the 0 is a digit of the product, then a missing digit is predictable. 1674, let's say the student chose 7 and circled it. So add up 1 plus 6 plus 4, you get 11. The digits of 11 are 1 and 1, which adds to 2. Therefore, 9 take away 2 is 7. That's all for now.